So let's start. So this is a workshop on the array toolkit called Eigen, and we will go through uh, most of the basic stuff with Eigen. I will not do the sparse matrices, but they're kind of similar. So it will be a starting course of how to use array computing with Eigen. So if we start with, let's see here, some practical information here. So this is the first time I'm doing this course, so I'm not really sure how long everything will take. So this is you're kind of the first testers of this. But the idea here is this is the introduction part of the course, and in the first part here, we'll make sure that you have your development environment set up properly, and I will go through that as well. Then I will have a lecture on basic matrix, how you work with matrices. We'll have a coffee break at 10, and then we will be, I have opened up for you working on the exercises that I've provided, and I will quickly go through some of the exercises at the end as well to give some ideas on how the solutions to these are. And you will probably also know that you can do a lot of things in different ways in Eigen as well. And then at 11, I will go in more advanced matrix operations. And then we have lunch. After lunch, you will continue working with your exercises. And there are some additional ones that are more related to the last lecture as well. Then after that, I will have a shorter lecture on how you integrate Eigen in your own projects and some of the best practice ideas on how you work with Eigen, how you return matrices and vectors from functions, how you pass functions to pass matrices to functions, for example. Then we have a coffee break, and then I will go through how you can use Eigen in parallel application. So also please note that Eigen is not a distributed matrix library. So this is in itself, it doesn't support parallel processing. You have to do some of that stuff yourself. However, it has functions for compiling it with OpenMP. So some of the functions and the classes supports OpenMP out of the box. So that I will show some how that works as well. I will also go through, if I have the time, one of my applications I've been working on. It's not a parallel application, but it's a finite element application, and go through how that solver is structured. So hopefully you will have time to work on your own problems here as well, and I will try to help you out the best I can in that endeavor as well. So first we are going to look at where you can find information about this course. And hopefully you should have gotten the links to the course page. I will put it in the chat here as well. So let's see here if I put it into this window here. So this is the course page. On the top here, you have the setup section here, where you can find some instructions how to use Eigen on Cosmos, which is a Lunar resource. It's probably a lot familiar with many of the NAISS resources as well. So it's not, you will probably find some way of adding the Eigen modules here, but and I will show it here live as well. But these are the 3 steps to load the modules required for Eigen. CMake is optional, but Eigen, this is the important one. And you should have a G++ compiler available, and CMake if you need that as well. And it should give something like this as output here. And to validate, I have a small program here that we will run. And just to show how it works, I will do this on Cosmos itself. So here is, I have logged into the desktop here on Cosmos, and I just created a directory here It just contains my test file. And the first thing I need to load is the modules. So I'm just gonna move this. So I do ML was 2024A, like that. Then I do ML Eigen with an uppercase E. And then I can do a simple compile here. It should work out of the box. G++ ex0 .cpp minus O ex0. And that should be, so that is the way you can compile it if you have the modules loaded. On a Linux machine, it's very similar. So I will go to, so now I'm running on Windows here. But I'm running the Windows subsystem for Linux. So I have a Ubuntu desktop running here. And I have go into my directory here as well. I have a single file here, and I will compile that one as well. So I do here, you need to do a bit more steps. So ex0 cpp minus include user include eigen3 minus O ex0. So for some reason, you need to have this include here. It doesn't find it automatically. And should give you an output like this. So this is the way you compile it on Linux and on Windows as well. You can use a Windows development environment as well. Then you probably will have to use CMake and create a Visual Studio environment to do this. But as VSL is included in Windows, I recommend to use that to compile your examples. For Mac, as I don't have a Mac now, I can just show the instructions for Mac, but they are very similar to Linux ones. You can install the required software here with brew. And then you compile the same example here using this code here. So here you have the difference is use a local include eigen3 like this. And it should give the same output like this as well. Do all of you have a working environment?
I do, at least.
Very good. Then I don't have to spend too much time on this. But just let me know if there's anything, and we'll help you in the exercises as well. So let's continue here. This I showed you here. So a short introduction now. So why shouldn't you build your own matrix library? So if you're working with C++, you perhaps and also have learned object-oriented programming, and you're thinking, oh, object-oriented programming should be very easy to implement your own C++ library because you have all the operators and all that stuff that you can create really nice library, and you probably can. But there is probably a lot of people have done this before, and when you have a matrix library, there is so many quirks in C++ that you have to think about, and if you don't think about them, the performance will be really bad. And also you want to use libraries that are well tested. For example, the LAPACK and BLAS libraries, you want them as the underlying architecture to your application. And those are often highly optimized. And also creating your own, as I said before, if you create your own library, you probably will get some additional complexity that you don't think about really in your library, because there are things, as I said before, that makes C++ really slow if you don't think about it. So that's why we when I'm doing computer, I've tried to find matrix libraries that are designed by somebody else and that has those design goals in mind. And so I've used another library called Armadillo, which is similar to Eigen, which I also try. It's also very good. But I kind of got stuck on Eigen because it has a lot of facilities for integrating existing libraries and makes it really nice to work with. So what is Eigen? So it's one of the most popular libraries for linear algebra in C++. I say C++, there are other libraries, but in C++. Was a really cool thing. It's a header-only library. So really, unless you you can just put it in your directory and use it. There's really no linking required, except if you enable building it against the BLAS and LAPACK libraries. Then you have to link against those libraries. It's fast and easy to use, so it has many of the enables some of the performance optimizations of C++ when you're using this library without you having to do a lot of the work. And as I said before, it supports optimized packages like BLAS and LAPACK. It also has support for OpenMP for a lot of the operations in Eigen. Not all of them, but many of them. So when we build it on Cosmos, we build it with all the optimized libraries. So if you use Eigen on Cosmos and probably all the other NAISS resources as well, you will get an optimized version of Eigen. If you're using it like we in this course, we are not kind of super interested in performance, but more use it, you can just install the basic packages that come with your operating system. So now my light went out here again. Yeah, so how you use it in your own library is basically just you include the relevant header. So if you're working with dense matrices, you do include eigendense. There is also a sparse matrix, but you can select the things you want when you include. And the dense module includes all basic matrix operations that we are going to use in this course. And there are some other modules as well for different needs as well. But for this course, we are going to use only the eigendense include. Yeah, as I said, to summarize, it's very easy to get started with Eigen. Just to get started, you don't need any external dependencies. It's compatible with modern C++ standards, and it has excellent documentation as well, and also active community support. This we've gone through here a bit already, but I'm just going to skip it here, so I'll go quickly through it. So Cosmos at Lunark is one of the environments you can use. You can run it on Windows and Linux, Ubuntu, and Mac OS. If you want to use Cosmos, you should have applied for an account, and you should have gotten that, and you should be able to use our documentation here to log in. So I will open that one here. So Lunark here, you can go to documentation here and getting started here. You can log in either using SSH or you can log in using the Lunark HPC desktop, which requires you to use the ThemeLink client. And as I said before, if you want to load a module, load the environment, you use module load FOSS 2024A and the Eigen here. If you use CMake, you can load that as well. And then you verify using these here. It should be something like 13.3 on Cosmos. And this is a test file I showed you before. And here are some how you compile it. If you don't have a G++ on your Ubuntu machine, you can use apt-get install G++, and then you install libeigen-dev. The dev is important, otherwise you don't get the include files. Yeah, as I said before, you have to add, on Linux, you have to add include Eigen 3 here to be able to compile. Otherwise, very similar to what you do on Cosmos. Mac OS, you'd brew install the GCC compiler tool chains and then install Eigen as well. And then compiling it on Mac, you add std C++11 and then the include library, your source code, and then the binary you want to output. That's some troubleshooting here. Make sure that you have the Eigen and you're pointing the include to the right Eigen directory. So there should be a folder called Eigen with uppercase and then subfolder. The library should be in that folder. So so I have a question here. It's a header file only library. It could be that I'm not 100% sure here, but if you build it against the optimized libraries, it could be there is a stub of functions that are needs to be available if you have an application using Eigen. But to be honest, I think it's enough to have the header file. I will skip this demo here and go to first part here. So working with matrices and vectors. So let's go into the actual usage of Eigen. So matrix and vector type. So there are actually 3 types. I haven't covered. I won't go through extensively the array type as well. There is a generic array type in Eigen as well, but we're mostly going to look at matrix and vector types. All the classes in Eigen are template classes, so they can work with different data types. So you can have a matrix of floating point values, double values, integers, and so on. And all the classes are defined in the Eigen namespace. So if you include Eigen by default, you have to add Eigen : to all your calls. You can using namespace Eigen, which is in your production. If you do real work later on, you shouldn't using namespace Eigen. I will use this in my examples to make them a bit shorter, because it's a lot of extra characters to type if you have Eigen from everything here. So just be aware that my examples are a bit shortened, and that is not the recommended way of referring to Eigen. You should try to avoid using namespace, at least in your header files. In your implementation files, it's probably fine, but you can have some problems if there are similar types that clashes with each other. So you declare matrices in Eigen. There are many ways of doing. We're going to start with the matrices that are compile time static. So when you declare them, they can't change the size. So you start with Eigen : matrix. That is the main matrix type. And then you have a template declaration, which starts with the data type. So in this case, I have, let's see if I can get my, start with the data type here, and then the size of the matrix here, and then A here. There are some convenient type definitions in Eigen as well that you can use, because this kind of tends to be really long. So for static matrices, I think there are 2, 3, and 4 predefined. So in this case, Eigen matrix 3D, that is equivalent to this declaration here with double. So the D suffix here, that is the data type. And then Eigen matrix double here, that's so the same thing. So this is just a shorthand of that. You can do vector declarations as well. And eigenvector double, then you only have to specify the length of the vector. And there is also the same convenient type defs here, vector 3D W. Also note that by default, a vector is a column vector. So Eigen stores data in column wise, not row wise. So by default, it's column wise. So this is equivalent to a column vector, but there is no explicit column vector in Eigen. There is a row vector. So that is yeah, to distinct, but by default, a vector is equivalent to a column vector. And if you want a row vector, you have to specify the row vector class. You initialize matrices. Yeah. So by default, if you declare a matrix, it's not initialized. So the data area for a matrix will point to any place in the computer. So it's the same thing as having an undefined array in Fortran. So you're not guaranteed to have 0 values in your arrays. There are several methods to initialize arrays. So if you have declared A here, you can do set 0, and that initializes the array to 0. Set 1, same thing. If you want to specify specific values, you use the double distance operator, stream operator, I think it's called in C++. So basically the same way that you use the stream libraries in C++, you can use the stream operator to feed a matrix values. The only difference here is that you don't use the stream operator between every value. So you use commas instead. So in this case here in D here, you have D stream operator, and then 1, 2, 3, 4, 5, 6, and so on. That will assign all the values of the 3 by 3 double matrix here. You can also, using vectors, you can assign them using the same notation as in C++. So you can do vector 3, and then you give the values that you want to assign the vector directly here in the construction of the vector. You can of course also use the stream operator here to fill the vector with values. There are some functions in that is not only available on vectors. So very much like the linspace in NumPy, for example, you can do v.setLinspace, and that will create 3 values between 1 and 2. So you can see here it will create 1, 1.5, and 2. There's also a method called setRandom that can fill a matrix with random values like this. There's also methods for accessing the columns and rows directly. So if you want to assign columns certain values, you can do d.col and then you specify 0. And also note that if you are used to MATLAB, everything in Eigen is 0-based. So here I assign column 0, the values 1, 2, and 3. And then there's the same thing here. You can do rows, d row 0, and then you add the values to the row. As I said before, there are several common type definitions. So for the fixed matrices, you can matrix 2D, that is a 2 by 2 matrix with the double data type, float, integer, and so on. And they're defined up to 4. Dynamic size matrices, I will come into that. It's a bit too bit here, but the ones have an X instead of the number here. Same thing for the vectors here. You have, these are predefined vector data types. So now I'm going to try to do this a bit live as well. So here I can see I'm running Visual Studio Community Edition. So this is using the Microsoft compiler. I have included some standard stuff here, and you can see also that I'm using namespace Eigen and using namespace stud, and that is just to make the examples a bit shorter and easier to type. So let's start with declaring matrices here. So now I'm going to declare a matrix A. And the first thing I will need to do is this up here. Double. And then you specify the rows and columns here. So 3 by 3. And then the name of the matrix here. So if we just do Snout A here and run this example here. You can see here that the output here is kind of just random floating point values in space. So before we use this, we need to assign values to it. And what you can do then is you can do A, and then we do 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. So here we use the stream operator to fill it with values. Now you can see you get the 3 by 3 matrix here filled with the numbers I put here. You can, of course, sometimes I try to write the code like this to just make it more clear that this is a 3 by 3 matrix. A vector you can declare the same way. So you do vector double. Let's see, we do 5 values and we call it B. Also note that if you print the vectors, they will have the shape. They're printed in the right. So if it's a column vector, it will be on 1 column and 3 rows. But it doesn't do any more fancy formatting by default. It just prints it out in the way they are in memory. So in this case, by default, it's a column vector. So you see you have 5 columns here. I can also of course, do, if I put row vector here in front of this, you will change this to a row vector like this. And then you can do matrix. Let's do a 4D, for example. Now it's a 4 by 4 matrix of doubles. I call it B. And instead of filling it with value, I can do B dot set 0 like this. And you see here that I got the 4 by 4 matrix here with zeros. There's also a way of you can instead of using the set 0 method explicitly, you can also do B equals to matrix 4D colon 0 like this. This should do the same thing. There is also, if you want to create an identity matrix, you can do it in one single go. You can do matrix 4D C equals to matrix 4D colon identity. Like this. So now you see here that I have a identity matrix like this. And there is also, of course, there are many ways of doing things in Eigen. You can do c dot set identity as well. Or did I? I redeclared it here, so that's why it. So basically, use calling the set identity is the same operation as assigning the matrix identity function like this. You can also do random matrices that you can do by doing, for example, matrix. Let's do. So in a very simple way, you can create a random matrix here. And by default, it goes from 0, -1 to 1. So, and you can, and also you have e dot set random here as well. And that is equivalent to the previous call as well. So you have a method and you also have a function that you can use. So the same thing. So that was the first one. So up until now, I have been, let's go back to my PowerPoint. Up until now, I've been using fixed size arrays. And in many cases, you don't have the luxury of being able to set a fixed at compile time fixed size. So you need a dynamic sized array. And that can also be specified. And it is done in a very basically same notation here, but instead of writing the actual sizes of the arrays, you put eigen : dynamic and eigen : dynamic as a second dimension here. That tells the Eigen library that this array will be dynamic in both the first and second dimensions. And then f here is the variable. And then you can set the size using the resize method. You can also set it directly on construction, give it a default size here. And the default for doing this is instead of using the fixed size here as in matrix 3D, you put an X in the declaration. So matrix XD, that is a dynamic matrix of a double type. Then you can specify here the size directly if you want. But you always have the method of resize that you can use to resize the array afterwards. You can resize the matrix using the resize method, as I said, so rows and columns. If the total number of elements stays the same, data is preserved. If the total elements change, the data is lost and must be reinitialized. So it's very similar what you do in NumPy. Does similar things when you do reshaping and resizing. So in this case, dynamic resize 1.9, preserved data if a dynamic was 3 by 3. Then we read 6 by 6, the total number of elements changes and then the data is lost. Yeah, as I said before, you have the row vector here, and these are basically matrices 1 by 3 or 3 by 1. So the default vector 3D is that is a column vector. Yes, if you resize, sorry, a question here, will all the data be lost? Yeah, if you resize a matrix to to the total number of elements, it will be lost. We can try it out live when I'm showing that in my live examples as well. You can do matrix operations on your matrices. If you use A plus B, that is a matrix addition. If you do matrix times the scalar value, that is will be broadcast to all the elements in A. Matrix multiplication is the normal multiplication operator. If you want to add scalar to every element, you can use matrix : constant. If you want to do element-wise operations, you need to use the array method of the array or the matrix to kind of get access to the array part, and then you can add element-wise to the array. You treat the array, the matrix as an array, not as a matrix concept. And there is, of course, the transpose method. There is also an inverse that returns the inverse of A. And if you want to do some component-wise operations, you can do that using the C-wise prefix. And there is a lot of these defined for many common math operations. You can also do it using, instead of using this method here, you can use dot array and then use the method that the provider on the array to do element-wise operations on the array that is the data structure in the matrix. So this have the same effect. You also have some vector operations. So you have S dot, so the dot product. You have cross product using the dot cross method. And this I already told you, so it's a bit redundant. And then you have reduction operators here that is part of the array object. So you can do sum, product, mean, norm. Max, Fortran has a max method here, but in Eigen it's called max coef, and that will return a max coefficient in the array, and min will be the minimum coefficient of the array. Trace will return the trace of the array, and diagonal will the diagonal elements of the array, and k dot determinant will calculate the determinant of the array. So let's do some coding again. So first I'm going to show some of the operations that you can do I showed before with lin-spaced. So let's do a vector 3D. And here you can do, I'll show you how you can do a C++. I have auto formatting on, that's why it jumps to the next line every 1, 2, 3. So you can initialize a vector using this notation here, which is the C++ notation for assigning values to an array. And then we'll do vector. And if I do v dot transpose on this here, it will, because by default this is a column vector. And this will transpose it and make it a row vector. So you see now it prints it out as a row instead of a column, which is the default. And then you can do vector double. So I do 10 elements. Then I do 2. And then if I want to create a lens interpolation between certain numbers, I can do that using the v2.send lens based. And now I see I have 10 values here, so I have to 10 here, and then I will say I want to go from 0 to 1.0. This. And now you can see here that I get automatic interpolation from 0 to 1 using this command here. Also, as I said before, you can initialize arrays by accessing the columns here as well. So the matrix 3D, D, and then I do d.col 0. Also, I can do, for example, I can, instead of using individual values, I can actually add a vector insert into the column like this. In addition to doing col 1, 4, 5, 6. So here I will insert an entire vector v here, which is 1, 2, 3 in the first column, and then 4, 5, 6 in the second, and 7, 8, 9 in the last column, like this. So you can see here that I 1, 2, 3, 4, 5, 6, 7, 8, 9, like this. And of course, I can do the other way around. So I can do d row 0, v, d dot row 1. Because it works out. What did I do wrong? Because it's okay. I do transpose. Like that. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9. You will also notice that if you do something wrong with your arrays, Eigen is really good at throwing good exceptions and assertions. So if you do something wrong, in this case here, a row is doesn't have the same shape as a V because it's a column. So then I have to do a transpose here. And this is not a costly operation, but what V returns here, the transpose method returns, is actually a view of the original matrix. So V will actually just, like you do in a number when you do reshape, it doesn't cost anything. I have a question on allocate matrices on the heap. I will get to that just in the next step. So the matrix XD, for example, that is a heap allocated array. But I will come to that shortly. Like that. So let's start again. And then, as I said before, matrix, for example, 3D, A. This is a fixed compile time array, and it's declared on the stack. So it's not heap allocated. It's fixed. And then you can assign that 1, 2, 3. This. If you want to have a dynamically allocated arrays, then you still use the same. You don't have to specifically allocate using new or make shared or anything. The matrix, the allocated data of matrix is hidden inside a matrix data structure. So if I want to do a dynamically allocated array, I do matrix, and instead of specifying a fixed number, I can do like this. So I do double, for example, and then I do Eigen dynamic, Eigen dynamic. I will show a short form of this as well here, and then I call this B. So this is the data for this array will be allocated on the heap. And to be able to use this, I first need to resize this. So I do resize, and then I do 3 by 3 like this. And then I just do e.set random. So you can see now it's random here. If I wouldn't do the resize here, let's see what happens. I think it will be mad at me. Okay, didn't do anything. If I do, but it also didn't print out anything. So okay, so but you still need to do this to be able to use it. Actually, sorry. No, so fixed size, they are by default allocated on the stack. If you do matrix 4D, this is a stack allocated array, or matrix, and the data is inside the data structure defined. But if you do matrix XDD, the data will be allocated on the resize on the heap. So, but the actual, so the management of the data inside is automatically handled. So when you go out of scope or you after the main has terminated, they will be deallocated automatically, but it will be allocated on the heap. So now I did this long form of declaration here. You can also have an array being fixed in a certain dimension and dynamic in another dimension. But you can, so if you want to make it short form of this, you do XD instead, and then C like this. This is a short form of a dynamically allocated array of doubles. And then I can do C.resize 4 by 4. Here is where memory is allocated. You can also do you can do reshaping of a matrix as well. So for example, if you do use the function, there is a method called reshaped, and that will let's see here. I'm going ahead a bit, so I skipped that. Now I'll do one short thing here. So if you have a vector, for example, vector xd is the same thing as when you do a v like this, and then I do v.set linspace. So if you have methods that gives a size and you haven't allocated the size of your vector or matrix, it will be allocated automatically. So in this case here, I have a dynamically xd array, and I said I want to have a linspace 16, starting from 1 to 16 like this. This will allocate the vector automatically. So you can see here that now I get a column vector here of 16 items automatically. So calling a function that with a dynamic array that hasn't been allocated will allocate it by default. What you can do now, if you have a vector like this and you want to assign it to, let's say we have our C array here that is 4 by 4, that is also 16 items. You can do this by using the reshaped method of a matrix or vector. So this guy can do C equals to V dot reshaped 4 by 4, like this. And this will interpret V as a 4 by 4 matrix, and it's a view of the matrix. So you can C will be assigned the values of this asset was a matrix 4 by 4. So in this case, it will be C like this. So you can see here that it, as you know, Eigen stores column-wise. So if you do reshape like this, you will get 1, 2, 3, 4 in this direction, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So stored column-wise. So that seems to check out. Then we have also, if you want to know the sizes of your arrays or matrices, so let's go here. Let's declare a row vector 3D v1, 1, 2, this, and then we have a vector 3D v2, 4, 5, 6. There are some methods that you can query to see the dimensions and the number of elements in your arrays. So first one is the size method. So v1 size equals to v1 this will report the total element of our array or vector. So in this case, 3. And we should have the same for vector 3D. So this is a row vector, this is column vector. They should have the same size. And they do. We can query also the number of columns or rows in a matrix and array. So we do this with a rows method and a calls method. And here we can see we have one column, I'm sorry, 1 row, 3 columns, which also should check out. And then we do the same thing here. We copy this one here over to V2. And this should be the other way around. And it checks out. So size is the total number element. Rows and columns are the rows and columns of your matrix or vector. I will let you have your coffee break now, and I will continue just doing some examples of matrix operations after the coffee. So let's be back here at 10:20. So before, let's see here. So I'm going to do, before you go into your own exercises, I will do some of the things illustrating the operations that you can do with matrices. So let's go clear this up again. So let's create two random matrices, matrix. So then we just going to show you some of the matrix operations you can do. So the first thing I want to create a C matrix that is the addition of A and B. What you can do, you can use C++ feature auto here to so you don't have to declare the return value equals to A plus B. And you can see here what the return value should be. But then we do south C. So this is the didn't show A and B, but I should print them out first here. South A. So you can see here that it's matrix addition here of A and B here. Then you can do, if you do like this, and now I'm going just to print them out here. Start A times 3.0. So this will multiply all elements in A with 3. So it seems to be correct. Then you can do matrix multiplication. So this is matrix multiplication, not element-wise multiplication. We'll come to that shortly as well. Good, like that. Then we have adding a constant value here. It's you can use the so if you see, we have A here is 0 minus 0.997, and if we add 1, you get something close like that. So this will add 1 to all elements of matrix A. Then you can also do, if you have a vector so vector 4D. You can do A times B. And this works because B is a column vector. You can see here you get the column vector back. If you would do, so for example, row vector 4D, B2, and we try to do this. And now you can see here, it's probably a bit difficult to see here, but if I paste the arrow in here, so if we want to do this operation here, we need to first do a transpose. Like this. So now, because we did transpose, they match. The metric multiplication is valid again. Otherwise, it already at compile time, it can detect stuff like this. So it has really good error handling. Then you can do, of course, you can do something like this. It's kind of obvious, A dot inverse. So no errors there. However, if you want to do element-wise multiplication of two arrays or two matrices, you need to use the dot array method of the matrix. So in this case, we do south component-wise. Then we do a dot array, make that method, times b dot array, like this. Then it will be element-wise multiplication. So that shouldn't be the same as A times C here. No, it's not the same. Yeah. So dot array enables you to get access to the array interface of the matrix, and then you can do element-wise operations on that matrix, or vector for that matter as well. And then we have, I'll keep the first one here. It's also possible to do, as I said, directly on a matrix, do component-wise operations. There are several ones of them. So if you do auto B equals to, for example, A dot C wise. So cwise is a prefix you can put on most of the functions that are available here, and that will enable you to call an operation on all the elements of a matrix. So in this case, I do apps here. Like this. And then we shouldn't have any negative values in B. Well, it checks out. You can do a similar effect of this here by using array dot apps like this. So you get the same thing, and it should be so. Cwise is kind of a shortcut, and then array is also a way you can do it a bit, but it's perhaps that looks better. I'm not sure, but you have both options available to you. Then we have let's see, we can do this. We have vector operations. So first, let's define 3 vectors. I have 2 three-dimensional vectors here, and we try different operations on them. So if we do first do so if you want to cross product, you do v1.cross.v2. Okay, it's should have. I'm just going to add a end line here as well. Then you get the one that is out of the plane here, so it should -1 seems correct. And then we can do the same thing with the other way around, and you should get the vector in a different direction. V2, V1. Yes, we have -1 there. Then we also have a dot product, also very similar. I will just paste it in here a bit quicker. Like this. And you should have 0 on the first one and non-zero on the second one. Yes. Dot product. And just a quick one here. Let's see, matrix for the K. And then there are multiple methods you can call on each of these methods to do reduction operations. So in this case, we have ksum, which sums all elements in the matrix, product of all elements, mean value, mean coefficient, which we discussed before, trace. But you can also do so we can nest them here. So you can do diagonal, for example, dot sum. Diagonal dot product. So diagonal will get the diagonal elements, and you can do the operation. You can chain them in multiple ways. It's also possible if you can do, like, for example, south k dot sum. Call 0 dot sum. So you can do multiple operations here, and you can say you can get the diagonal, you can do sum of diagonals and so on. So it's very flexible. You can nest them in many ways. And usually these kinds of chaining doesn't hurt performance because it's the diagonal returns a view of your K matrix, and then sum operates on that view. So basically, there is no copying going on in these operations. So now I will let you work a bit on the exercises. So I have, if I go to on the course page here, you have some exercises here for the first part, and this part here we do after lunch when I have had a lecture here on advanced matrix operations. So I will, if you have any questions, I can send you to a breakout room and we can discuss them together. Or you can work a bit on your own for the next, let's say, 20 minutes. So before lunch, I will go through a bit more advanced matrix operations in Eigen, mainly related to indexing, reshaping, and stuff like that. So, and also I will probably go through some of the exercises from the last lectures. You will also you can continually working with your exercises during the day in the slots that I have allocated. And try to go through them as well. So advanced matrix operations. So what you can do with existing matrices is that you can reshape them. And by reshaping, I mean you change the size without changing the number of elements. And reshape returns a view into the original matrix. So it's not a copy, it's a view. And that can be used to assign other matrices or do other, if you need a matrix to fit in a different function, you can use reshape to give that as a reference over. So for example, here we have, get the pointer, matrix A here, a 3 by 3. I can assign B here to be a reshaped version of A. That is a row vector in that case, so it will be a 1 by 9 matrix instead. Also have to say, when you reshape, you have to think about the matrix ordering, and that is you can that determines how the existing values will be interpreted as well. So note that it by default Eigen stores all the matrices in column-wise order. So you go column by column. Also, if you want to assign a reshaped version of your own matrix to the matrix itself, it's not allowed. But what you can do is that you can call the eval function on the reshaped to force the evaluation, and then it will create a copy, and then a new version of itself. So this is a trick you can use to, if you really want that kind of assignment. You can also combine reshape 1.9 and transpose it. So here you can see again, you can chain multiple of these methods together to produce a new matrix in this case, in D here. This is a dynamically, so this will be allocated to the shape of this expression here. I think I will go through all the examples later on, so I will skip the demos for now. And this I also discussed earlier. You can also extract blocks of existing arrays using the sequence function. So for example, if you do B sequence 3 to 5, it will extract a block from column 3 to 5 and column 3 to rows 3 to 5 and column 3 to 5. So basically you put them into the array access operator, and then you can assign certain parts of the matrix a value, for example. You can also assign them different matrices as well. You can also, there is a step function here as well. So if you add an additional argument here, it will do every other row and column from 0 to 9, for example. So that's very useful if you want to assign certain parts or a pattern of a matrix. You can use this the sequence function. There's also selectors you can use. So if you want to have all elements in the last columns, for example, you can do all rows, and last here will be the last column, and then you can do set constant 3. That will assign all the values in the last column to 3. You can also do last minus 1, and that will the second to last column to 4, for example. If you need to extract varied indexes from a matrix, this is very common when you do finite element, for example. You need to assign certain irregular indexes to certain points. You can actually use the normal vector operation in C++ to store the indexes, and you can use those as indexes into your matrix. I think my example I will show later, I've actually updated this, so you can have int here. You will get the compiler warning. You can, if you want to be completely correct, you should have. Let's see if I can write here. It should say index here instead. I will update that in my slides later. This is the index data type from Eigen. But you can use other data types here as well. If you have, for example, input from another program, you can use that to index here as well. Just looking at compiler can translate it. And then you can do auto D here, C index, comma index. That will extract a sub matrix here with these rows and columns. Another thing that you probably will do is you will need to solve linear system equations. And this will be a very high level overview in this course here, but there is a lot of this classes and methods built into Eigen that you can use for doing all kinds of different linear equation solving. I will give you a high level overview how you do it on a high level. So for small matrices, for example, up to 4 by 4, you can use the inverse operation directly. So in this case here, I have a matrix A here and a vector B here. And then I just do x equals to A dot inverse times B. Works fairly well on smaller problems. However, if you get to larger problems, you should use the decomposition methods that are built in, and it's very easy to use. So here are a 10 by 10 dynamic array with a dynamic vector, and what you do here is that you do column piv householder cure. That is the kind of decomposition you want to use, and then that has a method, and then you solve that for B. So A has a lot of these methods built in for creating these decompositions, and that decomposition has a solve method that you can call. And then you can check the error here by doing A times X minus B dot norm here as well. There is many of these here. This is kind of just general column piv householder QR. Works well for most matrices. full PLU, that is the most stable one, but is slower. LDLT for symmetric matrices, and householder Q are fastest but less accurate. So look at the documentation. There is a lot more of these available as well. There's a lot of options on those as well. What you also can do is you can reuse the decomposition from multiple right-hand sides. And you can do that by doing full PLU matrix XD. Then you have this object LU here, which you can reuse. So you give A as an input here, and then you can do multiple solving here. So if you have multiple right-hand side B1 and B2, you can do lu.solve and reuse that decomposition again. And it's also possible to, if B is an array of right-hand vectors, you can get a matrix of solutions on the left side here as well by doing lu.solve B. So that will solve for every right-hand side of the B array. So now I think I will do my demo. So let's start with some reshaping. So just give it then we can create a matrix B, auto B equals to A dot reshaped. And then we say we want it to be 1 row and 9 columns wide. And we just copy this here and change the to B here. Oh. Like this. And now it should have a B matrix with the same data as the A matrix. So here say 1, 2, 3, 4, 5, 6, 7, 8. And then you can see here that when you reshape it, it will go column wise. So that's why you see here that this is in the wrong order that we specified from the beginning, or it is the correct order. But if you look at it will go 1, 4, 7. Next column 2, 5, 8, and 3, 6, 9. So that is something you have to be aware of when you do reshaping. So that was that. We create the C matrix again, but now it's a dynamic one. And then we do so if we try to do reshaped 1.9 like this, okay, it worked anyway. That's good. Let's see here. Okay, that shouldn't have worked, but it did work. But the idea is that you should call eval here to make it work. Okay, I have to check why that didn't work, but okay. You can also do matrix XD if you want to have go back to the original one. So now we have a 1.9 here, and we want D to be a reshaped version of C. We can do reshaped 3 by 3 dot transpose. So we do combine the operations here. Now you can see this is a dynamic array. And if that array is assigned, now when you do this declaration here, it is not allocated. But because we assign this one here, reshaped version of C, D will be allocated and C will be assigned to D. So if we do a copy here and see what we get, we do D. And we can also ask it to see how the rows and columns of this one is. So we do south, and D size equals to D dot size. And then we do C dot rows. Now we do C dot D dot calls. So now you can see here that we have the new dynamically array XD that has been assigned from C, reshaped to 3 by 3 transposed. So you can see it is 1, 2, 3, 4, 5, 6, 7, 8. So seems to be correct. And then you can see also that there was an automatic allocation here because this was a dynamic array and we didn't give it a size, but the assignment here forced the assignment automatically. Let's do some sequencing. So let's create a 10 by 10 matrix. And we give it 0. So now we should have a so you can see you have a 10 by 10 matrix with zeros. Now we're going to do some matrix block operations on it. Sorry, not sequence operations on it first. So what we can do is we can do B, and then we use the sequence function here, and we do 3 to 5, comma sequence 3, comma 5, and we assign it a once array here. So that now we get the 3 by 3 blocks of 3, 4, and 5, 3, 4, and 5. So we need to assign it with a 3 by 3 matrix, which we can create, matrix XD once 3 by 3, like this. And let's see if we print this now again. You can see here that we started from 0, 1, 2, 3. So it's there, 0, 1, 2, 3. And then we have a block here, and we allocated these elements in the array, these values. And then I said we can do blocks that are irregular or with spacing. So then we do B sequence 0. We start starting point to end with step 2 sequence 0 to 9 with a step of 2. And that is equal, or we do, now we can call a method directly on this matrix. We can do set constant. And to be able to see how it works, we do a 2 like this. Then we print it out here again and see what we get. So now we have the first block here, and then we modify the matrix again. And you can see we set 2 starts from 0 and goes to 9 with a step length of 2. So you can see you get the patterns of 2 in the entire array. Then we can, of course, use our modifiers or the, what do I call it? The range definitions here. So B, let's see, all, comma, last. So now all rows and the last column, we set that to constant 3. And what did we get done? Then we print it out again. So now you see here that the last column here is 3s. And it's also possible to do B all, comma, last -1 dot set constant 4 in this case, just to also see that we can see it in the matrix. And you see the next last column is all 4s now. There is another operation that you can also use, which I didn't get in my slides here, but it's a method called block, and where you can a bit more quickly assign blocks of the matrix in a similar way using a sequence function. So if we have, let's do a reset of this one here. Now we create an A matrix to be a bit more creative, like this. And we create a matrix B that is 2 by 2, matrix 2D B, and we fill it with some numbers here. B 1, 2, 3, 4. Then we can do A dot block. And here you give the starting position and the size of the block that you want to copy in. So if you want the block in the upper left corner of our array, we can do 0.0. And then we say B is 2 by 2. So we 2 by 2. And then we can use a sign directly here. So A dot block equals to B, like that. So you can see here that we have 1, 2, 3, 4 on the top left corner. And if we want to have it in the lower right corner, we can do A dot block. And now we have to calculate. So 8,8 is the x2, and we have 2 by 2 again. And we say equals to B. And now you can see we have 1, 2, 3, 4, 5, 1, 2, 3, 4 in the lower right corner as well. So block is also a useful operation if you want to extract blocks as well. I mean, you can go the other way around here as well. You can do south block. Let's see. taking the middle now, 4 by 4 by 2 by, 3 by 3 to be original, equals 2 and line. And then we do a dot block. So that will extract a submatrix that you can use in other operations. I think 0, 1, 2, 3, 4, 5. Oh, we missed. If we move it down a bit, we can catch the 1 here. So just see here, 6 by 6. And you can see here that I get the block here that is here. So that is quite useful function to be able to work with blocks of your matrices. So let's look at some of the linear equation solving parts. So here we have two matrices that we random, or we print them out here as well. So it looks like this. Random matrix, standard matrix here, B side, and we're going to solve for X. So then we do, now this is a small matrix, so we can do the, and I'm very fond of using the auto keyword here, then we don't have to remember so much, so we can just auto X equals to A dot inverse times B. So we run this. We get the solution here. We should get, and we get B back here as well. So it seems to be working. So that was for small matrices. So let's go a bit bigger. Now we use dynamic arrays of our matrices instead. So we have 10 by 10. We set them to random. We have a B vector here as well. So the first thing we have to do is create on the fly, we create a decomposition. And if you do like this, we do auto X again equals to A dot, and you can see here that you can sort of call, you can see there is a pivot householder QR decomposition as a method of the A matrix clause. And then we have to specify, that returns a decomposition. And then you can do dot solve on that one, solve for B. And we can calculate error again, out to error equals to A times X minus B times more. Okay, sometimes you can't use order, so I changed that to vector XD instead. And now you can see that you get the solution here is X, and then you get error specified here. So to solve larger equations, you need to get the composition out, and that is a method that is part of the matrix clause. And then you can directly solve it like this. You can, of course, do, I will show later, you can create a decomposition object, which you can reuse, which I will do in the next example here. So let's see here. So now in this case, I create a matrix again, 10 by 10, but then now I create two right-hand sides, randomize those, and I want to solve them by, and also reuse the decomposition I created. So what I can do then I can create a decomposition object. So in this case, I know that I want to use the full pivoting LU like this, and then you have to specify the matrix type you're going to use. So in this case, matrix XD, and then we call it LU, full LU, and then we give it the A matrix as input. So now we have a decomposition, and now we can out to X1, so we can solve this here, and we can do that by using full LU.solve, and then we specify the right-hand side B1, like that. And we can solve for X2 using the same concept, LU.solve B2, like this. And we can just print them out like this. So let's see what happens. So I get two solutions from that. What you can also do is if you have multiple solutions you want to solve with the same decomposition, you can create the right-hand side as an array or matrix. So if we do like this, So now we have a right-hand side that has the same number of rows as A, but with the two right-hand sides. We can have multiple as well. And then we do the same thing in auto. X equals 2. So now X will be a matrix again. Oh, sorry. We don't have we have specified A already here, so we don't have to specify that here. And there we go. X. So now you can see here I have the solver now returns two columns here with solutions corresponding to each of the right-hand side in the B matrix. So this is quite handy. So that was my demos I want to do now. So what I'm going to do next, I'm going to go through some of your exercises here and just to give you an example how they can be solved. So I can put them here. And also my the GitHub repository has all the code that you need, and so you can check out and you can look at all the examples and the example solutions as well. So let's look at example 1. So it says create a 5-element vector and initializes with values 1 through 1. 1 to 5. And in the first example here, I just gave it a simple, not a shorthand, but a row vector, double, and then 5. And then I just did initialize the list in C++ and assign the values directly like this. You can have done that using integers as well. And here I have used a dynamic array, and you can do that with dynamic arrays as well. The only thing is that you need to have you need to have double curly brackets to make this work. So you can initialize a dynamic array using initialize list like this as well. And if we run this here, looks something like this. And then you can see you access the elements using brackets or parentheses as well. That's different ways to do it. The next example, number 2, we will go through here. The idea is to create a 3x3 matrix with all elements set to 0. Yeah, 3x3, you can have a shorthand matrix 3D. And then you do dot 0 here to 0 the matrices out. 2x4 matrix, you can do this. There is no shorthand for that, so you need to go to the template declaration here to find the data type and the size of the matrix. And then you can fill it with any values you want. Also, when I have done some of the examples here, I have used one, and that I'm trusting the compiler to convert to the correct floating point precision here. But in this case, W, you should, if you were correct, put them with 1.0. If you have floating point, 1.0 F. Number 3. Here we should create a vector with values ranging from -5 to 5. So what I did here is that I just checked here, and you need 11 values here. So I did a row vector v1 with 11 values in it, and then I set a linspace here that goes from -5 to 5. You can also use this syntax here to do this. Vector double 11 linspace 11 -5. So there is a method here, and there is also a function you can use. There's two options here. And then I have used some here. So I used the cy absolute to get the absolute values from the v1 array, and then from that I applied component-wise square root. You can, of course, also do v1.array.apps.square root as well. That give you the same results. And then you can, I didn't find any solution to do this, so I actually used a normal C++ loop here to loop over the indexes here and calculate the exponent of this and assign that back again. Calculate some minimum, and maximum values of the vectors. Yeah, you have them here. Max sum, you do the sum function method. Max coefficient to get the maximum value. Min coefficient to get the min coefficient value. Running this, we'll use following. Like this. So you can see here that I put -1 here, and I do absolute square. So if I would have run the square root of this, I would get not a number here. But in this case, because we did absolute value first, it works. That's number 3. And in the number 4, we should do some create 2 identical vectors and do some component-wise operation on them. So I have created 2 vectors here of the same length, row 1 and row v1 and v2. And then we add them together, v1 plus v2. And then we have component-wise product and dot component, well, the dot function here as well. Let's run this. Yeah, that's. And number 5, we have some matrix operations. And yeah, I showed them you here in my example in my lecture, but here you have, this is matrix addition subtraction, and this is matrix element-wise multiplication of all elements. So it's not the matrix multiplication, and the final one here is the matrix multiplication. So you can see these are not the same, they're not equivalent. This one here. Then we have number 6. In this case here, we have, this is just to explain that if you have a matrix A and vector B, you can multiply them directly because B is a column vector. And that is, it's 3 times 1. And you can multiply this. This will be 3 by 3 multiplied by 3 by 1. So they're compatible. And that's because by the definition, vector in an eigen is always a column vector. If that would be a row vector, you have to do a transpose to get this to work here. Number 7, here we should create a 4x4 matrix and calculate its determinant, inverse, and transpose, and also verify that A times the A inverse is equals to the identity matrix. So let's try that. So the determinant can be calculated by A dot determinant, the inverse A dot inverse, transpose A dot transpose. And then we calculate this here and see if what the value of that is. And how do you check that? And the interesting thing here is that there is methods here for doing this built into Eigen. So if you do A times A inverse, you can call a method called isIdentity. And that will return true if that is close to machine position identity. So you don't have to think too much about the accuracy here to do it as comparison. That is kind of built in. So let's see if we try this here. We run this here. You can see here A dot isIdentity. And you can also see here that there is a 1, 1, 1, 1, but almost 0 values here in the other part. So it's close to machine precision. And that's what this isIdentity can be used to check. Next, we have to see if a matrix is singular and have potential errors. So you can, of course, check that the determinant is less than 1 to the minus 10, for example, and see that it's singular. You can also, if you're using a decomposition, for example, you can use the method isInvertible here to check if it's singular or not as well. And there are some other methods as well, but these are just 2 examples of how you can use this. I think I will wait to those block operations here to after lunch here. If you want, you can continue working on your exercises, or you can get an early lunch. I will stay here until 12, and then we take lunch to 1300. So let's go through example 8. Here we should create a 4x4 matrix with sequential numbers. That's one here, very simple solution to it. And then, as I did before, we just use the block command here to extract different parts of the array, and or assign different parts of the array here. Then we have here D matrix. Let's see what. So in this case, we do the first part, we extract 2 by 2 block in the left corner, assign it to B. This is this one here. Extract 2 by 2 in the bottom right corner. This is this one here. And replace 2 block with a new 2 by 2 matrix. So this is this one here. We assign everything together. So the next, number 9. Three by 4 matrix will double here. Extract the second and third row, second row and third column. This is this part here. replace this one here. So you can use the stream operator directly here to assign a row. And then you can swap columns and arrays in different ways. The simple solution would be to create a temporary array, store the old column, assign column with the A column 3, and then set the 3 to the temp here. You can do it also using the swap method. So the swap method here is built into the arrays, and you can, so A column 2, swap A column 3. Then you don't have to go through the temp things here. Next we have number 10. You were supposed to create a 2x3 matrix, then return, resize it to a 3x2. And here we use, so 2x3 here, and then we create the B matrix that is 3x2, and then assign it reshaped 3x2. And then we create a vector element here of 6, and we reshape that into a matrix here using the reshaped of the vector instance, and assign it to a 2x3 double matrix. If we run this, it looks something like this. So you can see here that we have reassigned it to a 2x3 matrix there. Assignment 11, concatenation. Here we have, let's see here, we have two 2x2 matrices, these two. We create a C matrix that is 4x2. So here we use rows, columns plus B columns here. And then again, we can use the concatenation operator to add them together. And similarly, we can do the other way around, and then concatenate them together again. Number 12. Here we are supposed to do a bit of slicing operations. So we create a 5x5 matrix with sequential values. Could have done perhaps a bit quicker, but it works. And then we are supposed to extract the non-continuous rows and columns, for example, 1, 3, and 4, and column 0, 2. So here we create two indices that we want to access a submatrix. What we can do here that if I compile this one now, let's see here, I think I will get a compilation error. Okay, I compile just this one here. Recompile. Okay, sometimes I get here, but you can also do vector index here, which is the default index of the Eigen library. So if we do here, we put rows and columns here, we get the submatrix here, B, that has the indexes that we provide here. So if we, and then we had diagonal or anti-diagonal of the matrix. Here is an operation that we can't do with a method. So anti-diagonal we have to compute ourselves. So we actually have to create our vector here and then extract the anti-diagonal parts of that matrix by hand using a normal C++ loop. Otherwise, you can. There is a diagonal function as well. And then the idea is to create a tile pattern by repeating a smaller matrix. So I have created a smaller matrix here, 1, 2, 3, and 4, 2 by 2. I will create a larger dynamic array here that is 4 by 3 tiled columns and rows. And there are, of course, rows high and times call here to get the actual size. Then I loop over the rows and columns and use the block command to create this tiled matrix here. So you can see here I have these smaller tiles here that I loop over and I have filled the array with. '13 is linear algebra solving. So here was the idea that we create a symmetric 3 by 3. No, create a system linear A, solve the system with Eigen solver capabilities. Verify your solution by substituting back into original equations. So 10 by 10 here, solution vector 10. I create a full PLU decomposition, use the solve method here, and return that to X vector here. And then you can do some error correction here, and then we put it back into to verify that we have the solution, the correct solution. The 14 here, I didn't put in the lectures here, but there are some in the documentation how to compute eigenvalues and eigenvectors. So let's go to number 14. So here we have matrix 3 by 3 of eigenvector, which we will compute eigenvectors of. So here there is a special class called self-adjoint eigensolver, where we provide our array type, and then we create this object here, ES, and then provide A as input here. And you can check using the ES info here if the Eigen solution was found. Otherwise, it returns an error status here. And then you can extract eigenvalues here using the eigenvalues method, and you get the eigenvectors here by using the eigenvectors method. And then we can just print them out here, and then we can calculate here and see if it checks out here. And it seems to work. I will go through this image processing application at the end. You will have some time if you want to work with that as well in the afternoon. So then we continue along to the lectures here. So there are some best practices and points I have to make when you want to start integrating with Eigen in your own codes. And the first one I think is important here. When you're returning Eigen matrices from a function, return them by value. Because the actual stored values if there are small matrices, that is not a big thing. The compilers can optimize for that. Larger dynamic arrays, you only pass the metadata of the array, the matrix over. So the actual data is a pointer that is contained within this structure. So the actual data structure of the matrix data types are actually quite small. And also C++ has a special optimization feature now that will optimize this automatically for you, so there will not be any unnecessary copy.
So usually the way you do it is that you declare a function here, matrix XD. This function foo will return a dynamic array. And you create the array just like you would like do normally in your Eigen code, and you return it. And this will be there will no copying at all if the return value optimization is enabled. So you have to have I think it's C++11 above compilers for this to work perfectly. And then in your main code, you call it matrix XD B equals to foo, and there is no copying. So basically, you can create functions that create matrices and vectors and return them. So kind of a factory function. When you pass matrices to functions, you should always pass them as references. And also, if possible, use the const modifier to indicate to the compiler that the matrix itself is not modified in the function, which also enables some optimizations, and also checking your code for that you don't modify by mistake. So in this case here, I have a bar function that the only purpose of this function is to print out the A matrix. And you can see here that I have the matrix XD here as a data type, and then I have a reference operator here. So I pass the A as by reference. And in this case here, I have a matrix XDB 10 by 10, which I pass over to the function. And because of the const keyword here, the compiler makes sure that this matrix is not modified in the bar function. You can use it wherever, but you can't do operations that change the value of the matrix. Yeah, this is just an example of a real function by value. I'm going to just duplicate slide here. I skip this one. So here is a more real example here. So I have a simple element function that will return a bar element, and it needs EX and EY in parameters, and the material property is EP here as the third. So it takes read-only parameters as input, and it returns a 4x4 matrix. So here I assign, this is just convenience thing to have shorter variables. And I use the matrices inside here to calculate E, A, and L, and then I create my matrix to be returned and do my calculations inside here and return KE. Also, this G matrix here is calculated inside here. The nice thing with the matrices in Eigen is that you don't have to think anything about memory management, because if you have a dynamic matrix, if G here is a local variable, if you compute something or work with that and then you return from the function, the dynamically allocated memory is automatically freed. So by using Eigen, you will get more memory safety in your application as well, compared to using C arrays that you allocate by malloc and free, or you have a new or delete in C++ as well. So they are very safe data types. Sometimes you need to access, you give the matrix to other libraries that don't talk Eigen, which is probably not many directly. So you probably want to call either a C function or a Fortran code in some way. And all matrices in Eigen have a method called data. And that returns you the raw pointer to allocated memory for the array. And this can be used to pass to C code. So in this case here, I have a double, in this case, I don't post that. I get the data pointer out. So A here is a dynamically allocated array of double. And so the pointer is a double pointer. And I can get that pointer using a.data, the data method. That will return you a raw pointer to the data. And with that, you can actually access this as a one-dimensional array. So as when you're working with arrays, they are not stored as in a way that you have a two-dimensional. It's always stored as a one-dimensional chunk of memory. And if you get the pointer back to it, you can walk that memory and access the data as a C array as well. So in this case, I'm working from I equals 0 to a less a dot size. So this array has dot size elements. And then I can just print them out. And this is the actual, I access this using the C syntax. So this is not an object, this is on a double pointer that I access using the C syntax. So as Eigen stores data as one-dimensional arrays internally, if you need to pass two-dimensional arrays to two-dimensional C arrays, you need to do some management here. So I can get the double data pointer out like this, a data. And the second, you also need to be able to access this using the C syntax. You need to also create a data pointer to point to the rows in the array. So here you have to set up the row pointers here to data 2D I equals to data plus I times a calls. And this will be the two-dimensional C array. And then you can do this. The important thing here is that you should not delete data. After you have done this, the thing you are responsible for is the raw pointer here. So delete data 2D, not data. Data is owned by the matrix itself. It's really important to distinguish that. So this is then you have a pointer that you can pass to functions that need a two-dimensional C array. So in this case here, I have a foo function here that takes a two-dimensional C array, rows and columns, and then you need to do some operations here like we did before, and then you can call this function using the data 2D pointer. And then we have to clean up data 2D, of course, here as well. So there are some massaging to do if you want to call other libraries that have a C kind of a syntax. That is also, if you want to call Fortran libraries, for example, you also need to do some of these stuff. Sometimes you need to you will get return const arrays, and then if you want to really make sure if you want to integrate those, sometimes you need to cast pointers, and then you can use this count double star here to remove the constness. But only do this when you are sure that the data won't be modified. So you override a compiler's own check. So avoid this if you can, and const correctness is a feature, not a bug. So to summarize here, return matrices by value, pass matrices by const reference, use data for raw data access, and then create proper interface for C-style libraries. And maintain const correctness when possible, and don't try to override it, because sometimes it's unavoidable because the APIs are designed in a way that you can't get through this. And also be aware of the memory ownership. If you create two-dimensional C arrays, you are responsible for the pointer array that refers to the Eigen matrix. So that's really important. So
So I'm going to look at some of the example code now as well. So to illustrate that it's really no problem to pass arrays over, return them from a function. In this case here, I have the hook function again. Looks like this. It creates a dynamic, internally a dynamic array D, or matrix D, and then it returns that D out of the function. And then I assign matrices here. I call this function that it returns a matrix which I assign the two variables here. So just to check that this is actually that there is no copying being done, I will actually use the data method on the D matrix here to check here what is the data pointer of D here. So I will just do inside hook. I will run this. You can see here that I have inside hook here. I have it's called 2 times, and I have 2 pointers here, one and the second one here. That is second call. So I will then do copy this here, and call this one here. So we can compare the different addresses of the data pointer. If I run this now, you can see here that the pointer inside is for the data of the matrix D is 210 here. And the matrix DP stress data member returns the same address. So you can see here there is no copying being done when you return it from a function. And the same is for the second call, also the same pointers. So that was that example, and then we go to 3 here. So here I have a function that has takes 3 vectors as input and returns a array out. And we look at this, how this is implemented. And it looks something like that. So I have const here on my input arguments because I will not modify these inside my function. So I can put them const. I pass them as reference here, so you can see the and sign here. And I use return value optimization to return out the matrix that I've created inside. So first I create some variables here to represent, to make the formulas a bit shorter. I have an internal array here, kloc. I create this like this. I create some additional variables here. I have a local matrix J here. I calculate this like this. And then I create my final stiffness matrix here by some matrix operations here and return back here. So KE will return back. All of these matrices here, if they would, now they are statically determined, so they will be automatically handled. But if they would be dynamically allocated, when this return is called, all these will be cleaned up automatically.
So let's see. So if I start run this one here. Yeah, this is the stiffness matrix of a bar here. And so this is the way I usually think when I design libraries that use Eigen as the parameters. X4. This the same thing. I skip this one. Here's a bit larger example that I have been using. I'll just do. These are not very complicated. I will show you more advanced solve this afterwards here. So here I have a topology array, and this is picked from an example we have in Python, and the topology here is 1 based. So the first thing we need to do to fix this is to reduce all the numbers here by 1. And to do this, because this is a matrix here, we need to use array here to access the component-wise methods here. So what we do here is e of array equals e of array minus 1. So that will decrease all the values in this array automatically. I could have done it manually as well, but because this is copied from the example from Python, I chose to do it like this. I create a global stiffness matrix here dynamically. I zero it using the K matrix :0. I create a force vector. I zero it. Then I set my forces that I have on the system here using direct access to the matrix here. I could have had a column vector here as well. I'm not sure why I had assigned this one here. Okay. Some other parameters here. And then I have my element coordinates in 2 matrices like this. And then I loop over here for I equals to y ex rows. And I create the stiffness matrix for each element in this system. I call an ASM routine here. And here is some difference here. So this routine actually modifies the global stiffness matrix. So if you look at how this is implemented now, you can see that I have a const matrix topology that is not modified inside a function. I have a matrix K here that doesn't have a const designator, which means that it will be modified inside a function here. And I have a local stiffness matrix here that is as an input here. And that is not also modified, it's used inside here. But you can see here that I use K and I assign the global stiffness matrix here using the indexes here. And then I do plus equals, and then this like this here. And then I do some other stuff here, and then I calculate the solution. Matrix is here. Where do I solve this? Yeah, then I have the solve function here, which takes the global stiffness matrix, the force vector, the boundary conditions, and these are the vectors that are output parameters. So same thing here. We have const matrix for all the input variables that are not modified inside here, but we have A and R are return values. So those are not const, and all parameters are passed by reference. And then I just print out the results here, and then I loop over here. So this is one example of how you can use it in your own applications. And then we have I think I have done those examples here, yes. So think I will continue on. So the next part here is how you can use Eigen in parallel applications. And as I said before, and I'm talking about all day here, is Eigen provides efficient array and vector data types. It's, however, not a distributed array library. So you need to do the parallelization yourself, especially if you need to work with multiple nodes. But it will use the underlying optimized libraries if they are there. And many of these libraries already do the parallelization themselves internally in a node. So they can do multi-threaded computations. When you pass the data, you communicate with your library, you will need to use the .data method. That is the pointer that you pass to MPI libraries and other libraries that you want to communicate with. And also to note here that many of the operations in Eigen can use OpenMP, which will enable you to do for certain operations, you can actually get really good performance. So those parts of Eigen that can do OpenMP are general dense matrix products. These are OpenMP enabled. The partial PIV-LU decomposition can use OpenMP. Row major sparse times dense vector matrix products can also use OpenMP. Conjugate gradient with lower upper. There are some other algorithms as well. So I have a question here about Eigen init parallel and a related function is purely configuring the threading thread. Yes. And also if you have a modern C++ compiler, it's also not necessary to call the init parallel. It will be handled automatically as well. It's more if you want to explicit control, you can use that function. But it's not all functions that are OpenMP enabled. So it's not just by using Eigen and enabling OpenMP, you will not get acceleration for everything. So one simple example here I tried out is to, as I said before, matrix multiplication is OpenMP enabled. And you can do this very simple. So you can just set OMP num threads as a variable or directly in your code, and then you do matrix XDC equals A times B. This will perform be accelerated using OpenMP by default. And I just did some tests here, and so on a 20,000 by 20,000 matrix, doing some threads here, and it scales quite good without any additional work for me. So basically just running the command or the statement will produce this scaling. Of course, you need to have really large matrices for this to be useful because you need to be, there is a lot of overhead with the threads. So you need to have significantly large work packages to be able to take advantage of it. And then I have, let's see if I can open. Yeah, so what you also can do is, so I implemented a very inefficient way of just illustrating this. So I have a custom matrix vector multiplication. Takes two variables A and B as input, and then some input here. And then to actually handle this implementation internally, I just extract the pointers directly from Eigen. And then I do my own implementation here, working on the data that is in the Eigen arrays. So in this case, you step out of the Eigen and you do your own implementation here. And then the key is to use the I
I'll get my pointer back here. I have to point with the arrow here. So here you do everything manually, and I did some tests here. An MP implementation, Eigen implementation time. So this is the vector. I think I actually made a mistake here, but anyway, this is the kind of on a high level. You can always get access to the data and make your own implementation using Eigen's OpenMP and the underlying data structures. Yeah, using Eigen with MPI. So Eigen is not a distributed, as I said before. I have to highlight that again. And you do MPI for distributed memory parallelizer. So Eigen arrays is stored in a 1D memory layout. And you as a developer have to kind of handle the data distribution yourself. And I have an example here that I have implemented. I haven't extensively done performance on the but basically there is okay, a question is here as using a built-in library. So our experience we bind to other BLAS LaTeX libraries. Yeah, you have to test it, but my experience, the matrix is using the Eigen library of that is built on Cosmos. So it uses the underlying BLAS libraries there, and that's why I got the good performance in the. Let's see here. If we go back here to this one here, C equals A times B. This is built with the BLAS libraries on Cosmos. So the performance is as good as you get the libraries you have underneath. And then I will go to Cosmos. I hope you can see the text here. So I did a matrix. Let's see if I have the slide. Here I divided the matrix up into rows, and so this is matrix vector multiplication, and the vector is broadcast to all processes. Each process computes a partial result. So basically doing like this. And this is not there are much better ways of doing this. It's just kind of to illustrate how you can use it together with MPI. So I implemented a class in C++ here that handles this distribution. So I have a local matrix here that I use the Eigen arrays with. So I have a matrix XD local and a local result. And then I divide up here, resize these here to the, so when I instantiate this object, I give it rows and columns, and then it resizes the local matrices according to the size of the global matrix. Randomizes the array. And here I do the local multiplications here. So I multiply the row together with the vector, the local vector part here. And here I use the Eigen's own matrix multiplications. So I use this internally inside the MPI application. And then I have a print results function here that gathers all the results and prints it out. And you should avoid doing that because you don't want to gather everything all the time here because that takes memory. But the idea here is that when you call an MPI function, you call it with your matrix and you pass the data along here. And then you can use the size here to query the size, but the data is the key here to communicating with MPI. And then I initialize here my MPI. I create my distributed matrix like this. I randomize it. And then I create a random X vector here, which I want to multiply with, randomize it. I broadcast the data here, and the same thing here, broadcast x.data, that is what I want to pass along, matrix size. And then I call the multiplication here and multiply with x. And then I have some calls here. So you can use, I think Eigen should be seen as a building block for building MPI application. You still need to do all the optimization work. For example, first touch of memory and stuff. You have to organize the memory correctly, and that is. But it helps you. The boring stuff like memory allocation and stuff like that is all handled completely automatically using this approach. So this was the MPI stuff here. Yeah, so just to kind of give you a reminder, so I'm not the super expert in MPI here, that's Joachim, and we have discussed this a bit here. So for large data sets, you should never gather things in all data to one process, then you kind of defeat the purpose of MPI. I did only do this to kind of be able to print it out. Also writing the results to separate files in each rank using parallel or libraries and stuff like that. So, but you can use Eigen as a very good tool to create parallel applications. It will handle all the array manipulation stuff, and it does it very efficiently as well. And finally, I want to kind of show a larger application that uses Eigen as well. So this is an application I wrote, or I'm maintaining, that is a structural mechanics application. It's not a parallel application, but it does computations in real time, and that's why I need a fast matrix library. So I can first show you how the application looks like. It's called Objective Frame. So this is a three-dimensional beam application, and the idea is that you can create a and then you can put a force on it. And then you can calculate in real time the deflections, and you can handle quite large problems. But the important thing is that you need to be able to do this very fast to be able to get 60 frames per second here. We can do that with coloring as well. So this is the application, and I will just show how this is implemented as well. And I'll switch to. So on the left side, you can see all the parts that it's built. So the general architecture application is built around several libraries that are connected together to form a user interface. And in the user interface here, there is one important code that is called do feedback. This is the when you put the force on the structure, it makes the first calculation, and then the compensation, then you reuse that to be able to do this real-time updating. So the beam solver is created here. So in this part, you don't see a lot of matrices. And then we have a beam model that we assign to this solver. We add the tactile force here, and then we execute the solver a first time.
Then we have some error handling here. Then we compute the forces and update the model in real time. And then if you have already done a first calculation, it continues here to recompute and update. So this is continuously done 60 times per second. And then it computes the forces again here. So if we go into this solver, it's implemented in the solver library here. And we have, let's see here, class view. I've implemented a sparse solver, so it uses sparse matrices from Eigen. And so here I have implemented everything. I'm usually try to think a lot in object orientation. So I have a sparse solver class here that handles all the requirements here for my code here. So the setup here, the solve and the recompute parts are implemented here. I also have some other function calls here that can be, so you can use this library with function calls as well. So if we go in here in the setup here, I have done some type definition, so they are not that long here. Let's see here. What I do here. So here I do some resize operations. I clear the system list here. And the thing is that when you do with sparse matrices, you need to kind of fill them up. They don't contain any values from the beginning. They're assumed to be 0. And then you have to build them up step by step. So what I do here, I reserve how many non-zeros approximate I have. And then I create index sets here that I need to for the assemblation. And then I loop over my sparse iterator to set everything up here. And then I set them, the sparse matrices like this here, using this row, column, value triplets. And that is built into Eigen as well, so you can use that as well. Then, because this is a finite element solver, there is some massaging to be done to handle boundary conditions, which is done here. And then I call, I have a solver here that is a decomposition, which I call here, compute. And then I also check the error here. And then I solve for the system matrix, compute the deflections and the reaction forces here. I also have several function that is designed the same way. So I try to use const everywhere to make sure that I don't modify anything in the structures or in the subroutines by mistake. Also, every time there is something that's modified, they don't have the const here. And then I have collected everything into something called a beam solver. And this is a solver that takes the model that is defined and creates the input to the sparse solver at some point. So execute here. So here it reads the beam model, and beam model is constructed of a node topology. There is materials added into. There is nodes, elements, loads, and you can see here this is it's an object-oriented model of a beam set. And then I iterate over this. So here I create up the matrices I need for the computation. And then I loop over the element sets here and create all the necessary matrices I need for the finite element solver. So I loop over the model here, and here I call the element functions here with the parameters. So these are all Eigen matrices. And you can almost go from a MATLAB-like syntax to C++ using Eigen. It's really nice. So these are, I have a similar library in Python that uses the same kind of notation here, and it's very easy to convert from Python to C++ using the Eigen library. So this is how I implemented this in my code here. And I'm really impressed how well Eigen performs. And these calculations are done at least 60 times a second when you work with this application. So finally, I will do the final exercise as well, just to show how that is implemented. And then I will open for questions. So in the final question here, I wanted to show a more practical application here, that how you can use Eigen, for example, to process grayscale images and implement basic operations like brightness adjustment and contrast enhancement, and do a simple blur filter here as well. So what I've used in this example here is the image library. It's a very header-only image loading library based on STB library. And what you can do here is you can create an image, and then you can load that image, and it has a function here that you can get the matrix directly out of that library. So I have this in my code here as well. So I have this image library included here. And then first thing I do is I create an image GD image, and that is J stands for grayscale double. And if you read that in, it will convert that automatically to a grayscale image. And then I get the matrix back from this image here, which I will use for my calculations. And the first thing I will do is adjust the brightness and contrast of that image. So I have a function here that I've implemented that takes an image as input, const of course, by reference, and it has two values like this here. And I convert this array. I want to do component-wise operations. I don't want to kind of do loops. I want to use the built-in functionality of Eigen. So what I do here is I do Eigen array xxd result. So this will be an array that I operate instead of. So in this case here, I do result equals alpha times result, which is for the contrast. And then I apply brightness, result equals result plus beta, which is this one here. And then I make sure that I clamp the values from 0 to 1. And then I return the result as a matrix. And I think this will pass the data array over, so it will not reallocate anything. It will work directly on the matrix. And then I have the assign it to matrix XD here. And then I want to kind of save this to an image. And the thing is that the image library is can't go the other way around. So you can't take a matrix and create an image by default. So what I've done here is I have implemented a copy to image function that takes an Eigen matrix and returns an image. And really old style school loops here. So I create this one, I resize that to the matrix rows and columns. I just loop over and set the values of the image directly, and I return the image. And now I can save this image again. And that will have an image that is brighter here. So let's see if I can run this here. So if I go into the folder of that,
You can see here, this is the original image. It's a picture of the moon. And so I load this image in, and then I do brighter. So this is the brightness calculation, and I saved it out again. In the second part here, we will apply a filter. And same thing here. I have created a function here, apply Gaussian filter. It takes the matrix in, which I read in as an image. Put some parameters here. Same thing here. The Gaussian filter is a bit more complicated implemented. So here I have an additional function here. So I have a Gaussian kernel function as well here that creates the actual image kernel that I will operate with in this function here. So if we continue here, we have this one. So basically I create a matrix kernel and I initialize it here manually using normal loops. I couldn't figure out any good way of doing this just with Eigen functions in this case. And then I loop here over the kernel and apply the kernel to this here. I saw some implementation of this here using this internally using blocking things, but then you get problems when you get in the outer part. So this is actually the simplest form I could find here to do it. And then I just return the result. So you can see there is no memory allocations anywhere. I create the kernel. The result here is the image coming in here. This is a matrix by reference. And then I return the modify image. And then I save the part here again. So this is how you can use it in your own applications. It's really nice. I mean, you haven't seen any new or malloc anywhere in this code. Everything is done by Eigen automatically. So that was actually what I had for this workshop here. So to summarize here, let's see here, go to this. Yeah, I only had that one. Yeah. So I will stop my recording.